In this video, we are going to apply what we learned from previous videos on the differences and the effects on enzymatic kinetics of different types of inhibitors and solve the following problem. So here we are given a double reciprocal plot or Lineweaver Burk plot, and we are asked to determine the type of inhibitions and inhibition constants for 3 different inhibitors. So we will start by determining the kinetic parameters Vmax and Km in the absence of inhibitors. So let me write down the equation that describes the double reciprocal plot so that we can use it for our calculations. So from this equation, we can see that our maximum velocity can be determined from the y-intercept of the curve. So this is my y-intercept in the absence of inhibitor. And here I have each of my tick is 2 units of y-axis, right? So Vmax in the absence of inhibitor will be 1/4 or 0.25 micromoles per minute. Micromolar per minute. So Km now, in the absence of inhibitor, can be determined from the x-intercept. And x-intercept in the absence of inhibitor is right here. It will be minus 0.8, and so my Km will be minus 1/x-intercept. And so it will be 1.25 millimolar, correct? So now I will proceed to the calculations for the inhibitors. So we'll start with inhibitor A. Inhibitor A. Let's analyze the line that describes the kinetic parameters of this reaction in the presence of inhibitor A. It looks like being completely parallel to the corresponding line in the absence of inhibitor. And we know that this happens when our maximum velocity and our Km are decreased by the same factor. And this is a case for uncompetitive inhibition. So we can determine the inhibition constant through the ratio of our maximum velocities, apparent and the one in the absence of inhibitor. So we know already maximum velocity in the absence of inhibitor. So now we need to determine our apparent maximum velocity, for which we need to determine the y-intercept again, which will be 12, right? So we need to have 1/12, and this will give us maximum velocity in the presence of inhibitor. And 1/12 is 0.083 micromolar per minute. So we see how the rate dropped, right, by the presence of inhibitor. So now we need to determine alpha prime, which is the ratio between the maximum velocity in the absence of inhibitor and apparent maximum velocity. So it will be 1.25 millimole, 0.25 micromolar per minute over 0.083. And so we find that alpha prime is about 301. So alpha prime is also 1 plus inhibitor concentration divided by the inhibition constant. So from here, we can determine our inhibition constant, or Ka, right? Because we know the name of the inhibitor now. It will be concentration of inhibitor, the total concentration of inhibitor, of course, over alpha prime minus 1. And if we plug the numbers here, the inhibitor concentration is given, 20 millimolar, divided by 2, it will be pretty much 10 millimolar, right? So now, for the second type of inhibitor, inhibitor B, I'll use pink. So for B, the shape of the double reciprocal plot, the line of the on the double reciprocal plot crosses the y-axis at the same value as in case of no inhibitor. It means that maximum velocity is not changed by the presence of the inhibitor. But Km, the x-intercept, the absolute value for it, gets smaller. So it means that Km gets higher. And we know that this is only possible for competitive inhibition. So inhibitor B is a competitive inhibitor. So we can calculate apparent Michaelis-Menten constant, again by analyzing the plot and calculating the x-intercept. And it will be 1 over 0.2, 0.4. So it will be about 0.3. Let's have 0.33, right? About so. So it will be pretty much 3 millimolar. And so alpha, which is the ratio between apparent Km and the Km in the absence of inhibitor, will be 3 over 1.25, which will be equal to 2.4. And so we know that alpha is equal to the same kind of expression, right? So now we need to have B here and just KB without prime. And so we can calculate actually KB, which will be our, let me calculate KB here. KB will be concentration of inhibitor, which is 20 millimolar, divided by alpha, 2.4, minus 1. So now it means that we need to divide our inhibitor concentration over 1.4. And so it will give us the inhibition constant about 14.3 millimolar. And finally, we have inhibitor C. And inhibitor C has the same x-intercept as our no-inhibitor double reciprocal plot, but the maximum velocity, the y-intercept gets higher, so the maximum velocity gets smaller. And we know that this is actually the case. Let me see. I want to erase that. So this is the case for a special case of mixed inhibition called non-competitive inhibition. So C is a type of non-competitive inhibitor. And it has apparent maximum velocity equal 1/10, right? Yes, 1/10, 1/10, which is 0.1 micromolar per minute. And so alpha prime for this case will be equal to the ratio between between maximum velocity and apparent maximum velocity, which will be 0.25 over 0.1. That would be equal to 2.5. And so it will give us K prime for C as 20 divided over 1.5, which will be equal to 13.3 millimolar.